At the next step, we are going to use the phasor diagram to analyze a series RLC circuit. Right? It's a circuit like that. We have an AC EMF device in here, which is connected to a resistor, inductor, and a capacitor. And so, of course, the more complicated circuits are also possible. These might be connected in parallel and things like that. But this series circuit is enough to understand the basics of the AC circuit. So as a result, we are going to talk about this. So I'm going to talk about the phasor diagram for the resistor only in here. But let's just look at it. Look at the circuit and let's see which kind of quantities are there. So first thing is that, of course, we have an EMF of the EMF device, which should be expressed as a vector in the phasor diagram. There is a current that's flowing, so therefore the current is also a quantity that we will represent on the phasor diagram. And for these devices, we can talk about the potential drops. So I'm going to represent these potential drops by VR, VL, and VC. So that's the potential drop on these devices. So I'm going to investigate all of them separately. So as a result, we have also these quantities, the potential drops on these devices would also be represented as vectors in the phasor diagram, right? And we would like to understand the relationship between all of these. So the first relationship is the Kirchhoff's loop rule. Which basically says that the EMF is equal to the sum of the potential drops on all of these three devices. And this is basically is a summation of the time-dependent expression. So each of these are basically are amplitude multiplied with cosine of omega t plus a phase, where the amplitudes and the phases are different. So this is the part where handling the trigonometric functions are much more difficult than using the phasor diagram. And that's why we need the phasor diagram. So what happens is that if that's the case for the real quantities, then I can also express that relationship in terms of the phasor diagram like that. So as a result, we have like 5 quantities represented as vectors on the phasor diagram. They are all rotating together around the origin. And at any moment, I can express the relationship between them like that. So basically, the EMF as a vector would be a vector sum of these 3 potential drops. So that's one of the things. The second one is, of course, each of these devices have the same current on it. So therefore, all of these devices, together with the EMF device, so they are going to be basically having the same current as the quantity. So therefore, all of them have the current as the common quantity. So what I'm going to do next is I'm going to find the relationship between the current and each of these potential drops, starting with the resistor in here. So I'm going to do that. And at the end, of course, we are going to find the relationship between the current and the EMF by using this relationship. So as a result, this is what we need to do. I would like to find the relationship between the current and the potential drop. So at this point, therefore, I'm just going to consider some kind of a resistor on an AC circuit. So there's a current passing over it, and I'm looking for the potential drop, so on the resistor. Let's just keep this in mind by what I mean by potential drops. I essentially mean that when I'm going along the direction of the arrow, it is basically the initial minus the final. So therefore, if the potential really drops, then this is the positive quantity. So therefore, we have like V of R is equal to I times R is in a real resistor, whatever the time dependence of these things are. So as a result, if the current is an amplitude multiplied with cosine omega t, I take the phase angle of the current to be equal to 0. In that case, potential drop would be R times I 0 times cosine omega t. Therefore, from here, we just read this to be the amplitude of the resistor, and you can also read the phase angle over there. So if we draw the phasor diagram now, this is y-axis. I'm going to draw the current as yellow. This is the current as a vector on the phasor diagram. So this has an angle of omega times t. So I have chosen the phase angle to be equal to 0. So that's basically an arbitrary choice. But since the current is common in all of these circuit elements, this is a nice simplifying choice. And the potential drop, well, in that case, let me use a blue color for this one. The potential drop, therefore, is a vector like that. This is going to be in phase with the current, meaning that they have the same phase angle. Right? So therefore, we say that the let me write it down like that. Current and VR are in phase in the phasor diagram. Which means phase difference, the difference between the phases is equal to 0. Right, so that's the first relationship among the phases. So we talk about the phase difference and then the amplitude relationship, but you can see that here the amplitudes are related in the same way. So I think I need to erase something in here, but let's just forget about it. So therefore the amplitude is basically I0 multiplied with R. So this is the amplitude relationship. Or I can basically divide this amplitudes by root 2, and in that case I can express this relationship in RMS value. So therefore the RMS value of the potential drop on the resistor is equal to the RMS value of the current multiplied with the resistance. So it doesn't matter in whichever units, quantities you use, the proportionality between the potential drop on the resistor and the current have the same value, same relationship. Basically, the voltage divided by potential drop divided by the current is equal to the resistance. So that's the Ohm's law in AC circuits. We also need to talk about the average power, right? So this is basically equal to 1/2 of I0 times VR0. I don't want to rewrite this in terms of the other quantities, so let me also write that in RMS values it is given by these. So it's just the product of the potential drop with the current, obviously. So that's the average value. So on the phasor diagram, this also can be expressed. It's just the dot product of these two vectors. So I'm just going to express it like that. So even though both of these vectors are rotating, sorry about that, this is the average power dissipated on the resistor. So that's equal to 1/2 of the dot product between the current as a vector and the potential drop as a vector. All right, so there's a 1/2 in here if you assume that these vectors are vectors where their lengths are equal to the amplitudes. But sometimes people take the amplitudes, the lengths of these vectors to be the RMS values, in which case we don't have this 1/2 in here. So I'll also talk about this case too, but if you want, I can also write that relationship. But to make this less confusing, let's just stick to the convention that the lengths of these vectors are just the amplitudes. So as a result, in that case, the average power dissipated on the resistor is just the dot product of these two vectors. All right, so therefore, there are these three physical things. So one is the relationship between the phases. So on the resistor, the current and the potential drop are in phase. Phase difference is 0. The second one is the Ohm's law that basically relates the amplitudes of the potential drop and the current. That's the Ohm's law. And the third relationship is the average power of energy dissipated on the resistor. So for the capacitor and the inductor, we are also going to look at these quantities and see what happens there.